So the operational amplifier was designed as a tool that could be utilized by electrical engineers to perform what's called analog signal processing operations. Things like combining signals, subtracting signals, performing linear amplification, so making a small signal larger, attenuation, meaning making a large signal smaller. We can actually find out today that we can do calculus with signals as well, using an op-amp, all dependent on how we configure it, okay? So if Wednesday's class was about how they work, today's class is about how they're used in practice, right? So the first circuit that we're going to look at is called a buffer amplifier. So in a buffer amplifier, we have the following configuration. We apply an input signal to the non-inverting input pin. Then we have a feedback resistor placed between the inverting input pin and the output. I'm going to call this guy RF. And then we take our output voltage at the output pin. Okay. So if I apply my rules, no current flows into either of my input terminals. I can see very easily that the voltage present at my non-inverting input terminal is simply Vn. The voltage present at my inverting input terminal must then also be in because of our ideal op-amp rule number 2. And from that, I see that V out is simply Vn. Now you may be asking yourself, what's the use of an amplifier that simply returns your input signal as your output signal? So this amplifier is used to isolate signals because it has a very, very large input impedance. Okay, so effectively, if you have a small signal that isn't able to deliver a lot of power to a particular load, you use this kind of amplifier to send that signal to a later stage, and it retains its characteristics while using the op-amp itself to provide power to the thing that you're driving, okay? This amplifier has a voltage gain, AV, which is defined as V out divided by Vn of exactly 1. Where's your mask? This is our first amplifier. Fairly straightforward. Let's complicate things a little bit and start throwing some actual resistor networks and all that kind of good stuff in there. Okay. The next one that we're going to talk about is a non-inverting amplifier. It's very similar. So we're still going to apply our input voltage at the non-inverting input pin. We're still going to have a feedback resistor, RF, placed between the inverting input terminal and our output terminal. But the difference here is that we're also going to place a resistor, which I'm just going to call R1, between the inverting input terminal and ground. Okay, so it's similar, but there is a very distinct dissimilarity here that we need to take into account. So again, recognizing that no current can flow into or out of my input terminals, Norman, what's the voltage present at my non-inverting input terminal? Just the N. Bradley, Bradley, what's the voltage present at my inverting input terminal? Also Vn. Now I'm going to apply KCL at the inverting input terminal node. So I'm going to be adding together this current plus this current and setting them equal to 0. And what I'll find is I get Vn divided by R1 plus Vn minus V out divided by R2 is equal to 0. And with a little bit of algebra, I find that V out is equal to 1 plus R2 over R1 times Vn. Excuse me, RF, thank you. Thank you very much, Norman. And I therefore have a voltage gain of 1 plus RF over Rn. Or R1. Gosh, I'm get myself all wacky here with my nomenclature. Sorry. I want this right. So it should be fairly obvious to see that our buffer amplifier at the top is actually just a special case of the general non-inverting amplifier, where R1 is an infinitely large resistor or an open circuit. Okay? We can see from our voltage gain relationship that the non-inverting amplifier only amplifies signals, and the amount of amplification that it provides is dependent simply on the ratio of RF divided by R1. I'm mentioning all of these things because if you look in some of the old exams that I've posted, I like to ask a question about what could you do to increase the voltage gain of an amplifier like this, and the short answer is increase RF or decrease R1, right? As RF gets larger, the voltage gain goes up. As R1 gets smaller, the voltage gain goes up. Changing the value of the input signal doesn't change the gain, right? The output is simply a scaled version of the input, and the scaling factor is 1 plus RF over R1. Let's make a slight change here. So the next amplifier that I'm going to draw, and I'm making a point to say this as well, because I'm going to ask you guys to build one of these in the lab today. And then I'm going to ask you guys to build the next circuit that we're going to discuss, which is called an inverting amplifier. The only difference between the non-inverting amplifier that we just discussed and the inverting amplifier that we're about to is that we swap the location of where we apply the input voltage and where we apply ground. Okay, so it's literally the same circuit. oops, sorry, minus up here. But now we apply ground at our non-inverting terminal. We have our feedback resistance, R sub F. Here's V out. We have that same resistance, R1 here. But we apply Vn over here. So it's literally the exact same circuit, except we swap those two voltages. I'm applying op amp rule number 1, saying that there's no current flowing into the input terminals. Brett, what is the voltage V plus, my voltage present at my non-inverting input terminal? 0, because it's connected directly to ground. Absolutely right. Let me save it and restart because it's going to keep doing that thing that's going to be annoying. My apologies. Abby, what's the voltage V minus, the voltage present at my inverting input terminal? 0. Op amp rule number 2 tells us that whatever voltage we have at our non-inverting input terminal also shows up at our inverting input terminal. So we have 0 volts here. And if I apply Kirchhoff's current law at my inverting input terminal node, so that's adding that current plus this current, I get negative Vn divided by R1 plus negative V out over R2 is equal to 0. And with a little bit of algebra, this becomes negative R, sorry, R2 should be RF. RF over R1 times Vn. And therefore, my voltage gain is negative RF over R1. So my non-inverting amplifier can only serve to make my output signal larger, right? It is always going to be some positive number multiplied by my input signal. My inverting amplifier, however, by choosing different ratios of RF to R1, I can make the output be a larger version of the input that happens to be swapped in polarity, or a smaller version of my input that also happens to be swapped in polarity, right? So I get an increased functionality because I can both amplify and attenuate signals, make them larger and make them smaller, but it comes at the cost that I'm always going to get an inverted output. So the sign of my output is different than the sign of my input signal. Okay. The next circuit that I want to look at is called a differencing amplifier. So let's take our op amp. I'm going to have a feedback resistor. Let's just call this guy R. And I'm going to have another resistor R between the inverting input terminal and my input signal V2. Okay. Or let's call it VN2. On the non-inverting input side, let's have the following circuit. We have another resistor R. And then between the non-inverting input terminal, we are going to have a voltage source VN1. There are a couple of different ways that we can analyze this circuit. Okay. To me, one of the easiest is effectively just using the principle of superposition. Okay, that may not be obvious, but this differencing amplifier is literally just a combination of the non-inverting amplifier and the inverting amplifier put together, where instead of applying our input signal directly to the non-inverting amplifier, we have that little resistor network there. Okay, so if this current is 0 amps and this current is 0 amps, Skylar, what is my voltage V plus in this case? It's not going to be 0. So we're going to assume that VN1 is some non-zero voltage. And those two resistors oriented like that form a voltage divider network because none of the current can branch off, right? So if we have a voltage VN1 applied across two equal resistors, what's the voltage drop over one of those resistors? Half of VN1, exactly right. Brittany, what's my voltage V minus? 1/2 VN1. All right, you guys are catching on that it's always the same thing. Good. So if we apply KVL at that inverting input node, we're just adding this current and this current together, we get 1/2 VN1 minus V2 divided by resistance R plus 1/2 VN1 minus V out divided by resistance R is equal to 0. And we can obviously then just multiply both sides through by a factor of R. If we multiply both sides through by a factor of R, what we have left is 1/2 VN1 plus another 1/2 VN1 minus V2 is equal to V out. or V out is equal to V in 1 minus V2. So we can get the difference of two input signals as our output quantity. Okay. We could then, if we wanted to, feed that difference into another op-amp stage to make that difference larger or smaller as we see fit. This is analog signal processing. We are doing math on signals. Bradley. So that's an interesting question. Voltage gain, by definition, is the ratio of the output voltage to the input voltage. Well, in this case, there are two input voltages. So we have a specific voltage gain for each of the inputs, actually. The voltage gain for Vn1 is 1, and the voltage gain for Vn2 is -1. We could see that by just analyzing the resistor ratios or looking at the output signal itself. That being said, because voltage gain for multi-input systems is a kind of an odd duck, that's usually not something that would be asked. Okay, so that's why I didn't particularly bother to define it. Yes, sir. We always find V plus first in these circuits. Find V plus first and then use that to tell you what V minus is. Yeah. Any questions regarding our differencing amplifier here? So we've performed, Carter. Pardon? Okay, so let me draw something here real quick. So we have a voltage Vn1 here with respect to ground. We have a resistor R here. We have a resistor R here. And then we have the rest of the circuit. But we know that no current can branch off. So from the perspective of that Vn1 source, it just sees two resistors in series. And the voltage V plus is a nodal voltage. So it's the voltage measured at that node with respect to ground, which is just the voltage drop over that second resistor R. No, not a problem at all. Sometimes some of you guys forget that all of these quantities, V plus, V minus, V out, are all nodal voltages, and it sometimes gets a little awkward remembering what it means. So breaking it down doesn't hurt. Shaw. Yes, I'm sorry. I'll fix that. Thank you. V in 2. Thank you, Shaw. Any other questions regarding this guy? All right. So we just did a subtraction operation. Now let's do an addition operation. So this is going to be what's called a weighted inverting summer or adder. So let's say that I have an op amp like so. And I ground my non-inverting input terminal. I apply some feedback resistance, RF, between my inverting input terminal and my output terminal. And then also connected to my inverting input terminal, I'm going to have multiple resistors. So let's call this guy R1. Let's call this guy R2. And let's call this guy R3. And I'm going to have an input voltage VN1 corresponds with R1, an input voltage VN2 corresponding with R2, and an input voltage VN3 corresponding with R3. I could actually have more than this if I wanted to, but you'll get the gist of how it behaves just using a couple of input signals. So, same basic steps. Identify that no current is flowing into or out of my input terminals. Oren, what is my voltage present at my non-inverting input? 0 volts. McKinley, I understand that I'm beating this to death, but could you please tell me what the voltage is at my inverting input terminal? 0 volts. I'm doing this over and over and over again. I'm going to be, let's just say, disappointed if when you get tested on this, which by the way, this is not on the exam that's on Monday. This will be on your final exam in the class. But I'm going to be so disappointed in you if I ask you in one question what the voltage is at the non-inverting input terminal, and then I ask you in the next question what the voltage is at the inverting input terminal, and then you give me different results, it's going to hurt my heart. Okay, I'm trying to burn this into your brain. All right. So if we apply Kirchhoff's current law at this node, the inverting input node, we're going to be adding all 4 of these currents together. And so this is going to look like negative VN1 over R1 minus VN2 over R2 minus VN3 over R3 minus V out over RF is equal to 0, which I can rearrange as V out is equal to negative RF multiplied by VN1 over R1 plus VN2 over R2 plus VN3 over R3. McKinley. So when we're applying KCL here, we start at the inverting input terminal, which has a 0. So it's 0 minus VN1 divided by R1 plus 0 minus VN2 divided by R2, etc. No stupid questions. If you had a question about it, somebody else did, but they were afraid to ask. So this is called a weighted inverting summer because, so let's talk about the different parts here. It's weighted because each of the input signals is scaled by a different factor, right? So the VN1 term is scaled by a factor of negative RF over R1. The VN2 term is scaled by a factor of negative RF over R2. And the VN3 term is scaled by a factor of negative RF over R3. So all of the different terms get scaled by different amounts. So it's weighted. It's an inverting summer because the output signal is negative for positive input quantities. And it's a summer because we can see obviously that the quantity VN1, VN2, and VN3 are added together, or at least scaled versions of VN1, VN2, and VN3 are added together. Okay. We can change this from a weighted inverting summer to just an inverting summer by making R1, R2, and R3 the same value. Okay. So if R1 is equal to R2 is equal to R3, and we'll just call this R, V out becomes negative RF over R times VN1 plus VN2 plus VN3. Any questions on this guy? Bradley?
So if the voltage over here, AV and then equals RF over RN.
Absolutely. And in the inverting summer, so without the weights, or when all of the R1, 2, and 3 are the same, a voltage gain of negative RF over R is applied to all of the input signals equally. Any other questions? All right. So we have done amplification with the non-inverting amplifier. We've done amplification and attenuation with the inverting amplifier. We have performed the subtraction mathematical operation with the differencing amplifier, and we've performed the addition mathematical operation with our weighted and non-weighted inverting summers. We can't do multiplication or division with just a single op-amp. It requires much more complex circuitry. But we can do integration and differentiation. Okay. So I'm not going to put a name on this one yet because I always get them mixed up. So we're going to derive it first, and then I'm going to tell you what it is after we figure out how it behaves. So let's start with this guy. So at first, it's going to look like an inverting amplifier. Let's call this R. Here's our output voltage, and this will for sure be a time varying quantity. And then over here, we're going to put a capacitor. And this will be Vn of time. I'm going to call this voltage Vc of t. Actually, I'm going to use a different color because I've been using blue for that. So let's do this guy. And I'm going to call this current IC. So before we start on our analysis here, what's the relationship between Vc of t and IC of t? We have two different options, right? We have IC is equal to C dV by dt, or we have Vc is equal to 1 over C, the integral from negative infinity to t of IC of x dx, where I'm using this particular representation so that I don't have to worry about a initial condition on my capacitor. Okay. Those are just two of the equations that we developed, something along the ballpark of 2 weeks ago when we were first introducing the concept of capacitor and capacitors, right? All right, so even though we have a capacitor in our circuit, our ideal op-amp rules still very much apply. So the current flowing into my input terminals is 0 amps. We can see quite easily that the voltage present at my non-inverting input terminal is 0 volts, which means the voltage present at my inverting input terminal is also 0 volts. Hi, what's the relationship between VC of t and Vn of t? How do the quantities VC of t, the voltage drop across my capacitor, or did you say one or what? Okay. How do the quantities VC of t, the voltage drop across my capacitor, and Vn of t, the input signal applied to this system, relate? They're equal to each other, right? Vn, by definition, is the voltage drop between that input terminal and ground. Well, the other leg, or the negative, the inverting input terminal looks like ground in this case because it has a potential of 0 volts. So we can say that Vn of t is equal to Vc of t, and therefore Ic of t is equal to C Vn by dt. Everybody okay with that? If you got any questions, I'm happy to answer. We can perform Kirchhoff's current law at the inverting input terminal, just like we did for literally every circuit we've analyzed today, and find that negative Ic of t, so that's negative C dVn by dt, give me plus 0 minus V out divided by R is equal to 0. And from this, get V out is equal to negative RC dVn by dt. So this must be the differentiating amplifier because the output is a derivative of the input signal, scaled by a factor of negative RC. Anybody have any questions about this guy? All righty. Well, then our last one, I think I've got enough room here. We'll do it underneath there, actually. Our last circuit that we're going to analyze today is this guy. Do I need to go back to the previous page? Differentiating. So it's taking the derivative. So this circuit is going to be the exact same thing, except we're going to swap the placement of the capacitor and the resistor. So this is definitely going to be the integrating amplifier. That's absolutely correct. Let's call this voltage VC and this current IC. I'm just going to write down my relationships between current and voltage for a capacitor again. IC is equal to C dV by dt. And VC is equal to 1 over C integral from negative infinity to T IC of X. And we'll go through our analysis. No current can flow into either of our input terminals. The voltage present at the non-inverting input terminal must be 0 volts. And from this, the voltage present at the inverting input terminal has to be 0 volts. I'm going to do this slightly differently. Okay. Effectively, I'm still applying KCL at the inverting input node, but we can recognize, I hope, that this current is equal to IC. The current that I've drawn in purple, let's just call it I of T for right now, can be written as Vn divided by R. Everybody okay with that? What's the relationship between VC, my capacitor voltage, and the output voltage in this case? Anybody dare to take a crack at it? Exactly right. VC is negative V out. Does everybody see that? Okay. I'm going to write that guy down. So V out of T is then negative 1 over C times the integral from negative infinity to T of my capacitor current. But my capacitor current is simply Vn over R. And so slightly rearranging, I get negative 1 over RC integral from negative infinity to T of input voltage. So this guy, I didn't leave room at top, is an integrating amplifier. The output is simply a scaled version of the integral of our input signal.